Okay, so this is a brief video on taking combinations to the next level, and we're going to start out with a little bit of review. It's going to be basically the same stuff you did in the very first video we've done on this topic, where we put all the different types of counting problems together. But we're going to take it one step farther there at the end, so make sure you stick with me the whole time we go through this video. Okay, so first idea, you guys already know this, these are different than permutations because in a combination the order is not important. A group's a group, everybody's equal, there's no specific roles to fill, okay, there's no first, second, third place. Things that you might look for in a problem or words that they might use, ways of thinking about it, you're just picking representatives. Nobody's more important than anybody else. They might be on a committee and everybody has an equal vote. But there's no leader, there's no recorder, there's no president, anything like that. Instead of giving a first, second, third place trophy or a medal or a ribbon, the first, second, third place finishers all might get a participation ribbon. There's no reward for being first. There's no reward for being second. You're just getting the same thing that everybody else who gets a ribbon would. Now there would have to be a cutoff somewhere at who gets ribbons and who doesn't, but all those ribbons are equal. None of them are better than anything else. In the last set of homework, the permutation homework, I know there was a problem that talked about going to different stores. How many ways could you go to a different store? If it were a combination problem, you wouldn't really care the order that you went to the store. You just have the idea, as long as I get there, it's fine. I can go to them in any order. I can pick up whatever I need whenever I need it. But as long as I get to these stores, it's okay. Not that I have to go to Target first and then Walmart or whatever. You're just going where you're going, and as long as you hit all the places on your list, you're good. So that's kind of the idea we're thinking about here. First thing I want to do is review the formula. So this is how we write a combination, NCR. Okay, your formula is n factorial over n minus r factorial, r factorial. Okay, this second r factorial here, or just the r factorial, is what accounts for getting rid of all of the repeats. Because, like we said, order is not important. So say Johnny and Miranda and Lulu were picked to be a group. If it was Johnny, Miranda, and Lulu, or Lulu, Miranda, and Johnny, it doesn't matter. They're still the same group. So this, the r factorial, is getting rid of those repeat groups. Okay, so let's do this example here. 6, it's a combination, and we have 6 things, and we're choosing 2. I'm going to use our formula here. So it would be 6 factorial over 6 minus 2 factorial, 2 factorial. Okay, now I'll explain how to do the calculator shortcuts here in a minute if you haven't found them already. I'm going to do this one by hand. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1 over, this is really 4 factorial, 6 minus 2, so 4 times 3 times 2 times 1. And then that second factorial that's getting in the denominator, it's getting rid of the repeats, 2 times 1. Okay? What I want to do is I want to cancel out as many things as possible. So I'm going to cancel out the 4 factorial from both the top and the bottom. That gets rid of the 4, 3, one of the 2's and one of the 1's in the top, in the bottom, okay, in the denominator. These don't have pairs in the top to get rid of. You can only have one in the top and one in the bottom to cancel. So what we're left with is 6 times 5 over 2 times 1, or 30 over 2, which is 15. So the answer to this problem is 15. Now, you could use your factorial key or your combination shortcut in your graphing calculator. And scientific calculators have those too. You just have to look for them if you happen to not have your graphing calculator. They're typically under the probability button on your calculator, so look for that and see if you can figure out where they are. But in your graphing calculator, if you hit math, the math key, and then go over to probability, I showed you where the permutations were the other day, and permutation was number 2. Okay, the combination shortcut is number 3, NCR. Now, if you would rather use the factorial, okay, and figure it out the long way here like we did here, instead of using your shortcut, then you would use number 4. Factorial is number 4. Okay? So those are there if you need them. I would use them, really, if I had a difficult problem with big numbers to use. I wouldn't do it all by hand because it's going to be tedious and take some time, so I would just use the calculator unless it tells you otherwise. Here's a word problem. I need to send, and that should say 2 representatives from my class of 25 students to lead the school in the Pledge of Allegiance on Monday. How many different pairs of students could I send? Okay, so this is a combination because I'm sending representatives. Nobody's better than anybody else in this group. They're both going to go down there and they're both going to lead the pledge. So it would be 25C2. Choose 2. 25 students, I'm picking 2. Okay, so my formula would be 25 factorial over, I'm going to go ahead and do this in my head, 25 minus 2 is 23 factorial, 2 factorial. Okay, if I'm doing it by hand, 25, 24, and I can stop here, 23 factorial. This is really 23 all the way down to 1. That 23 factorial is going to cancel out the 23 factorial in the denominator. So I'm left with 25 times 24 over 2 times 1. That's really 600 over 2, which is 300. So there are 300 pairs of students that I could pick to go down and lead the pledge. Now, I'm going to do it slightly differently. Here I did the long way with the math. I could put it in the calculator. That's probably the easiest. But I'm going to use what I call the count down, count up. Okay, I have 2 spots that I'm trying to fill. And this is going to start out like the permutations we did the other day. I have 2 spots I'm going to fill. I have 25 people to pick from. So I have 25 options for that first spot and 24 options for that second spot. That right there would be a permutation. One of those students would be more important than the other. The first one's more important than the second because they would have to have order to it. To get rid of that, that's this factorial part, okay, that doesn't cancel out. Notice that it's a 2 and I had 2 blanks. It's always the R, which is how many things we're picking. So I'm counting down from the total that I have, and then I'm going to count up, and I'm going to start over here. I'm going to go 1, 2. I'm basically numbering those blanks, and that's going to give me a denominator to divide by. If you look, that is the exact same math that I have here, and it will always work that way. You count down in the numerator from the number that you're picking from, and then you count up in the bottom, and it should be whatever that R is all the way down to the factorial. So if that R were, say I was going to pick 4 students, that would be 4, 3, 2, 1 in the bottom. My top, I'll just write that. I had a group of 4 that I was sending. It would be 25, 24, 23, 22. Down here, 4, 3, 2, 1. That's the R factorial. And then the numerator is the reduced part, what's left after that other factorial in the denominator has been canceled out. Okay, so that is an additional to talk about, but the answer to this is 300. Okay, we're going to add another layer to this, and this is where it gets a little different, a little more complicated, where you got to think. We're going to talk about a deck of cards. Okay, so if you don't know, there are 52 cards in a deck of cards, and they have one of 4 suits that those could be. Okay, you have diamonds and hearts, you have spades and clubs. Okay, these are your red cards and those are your black cards. Okay, so diamonds, if you can't tell what I have here, I don't know if you're going to be able to read my handwriting any better. Spades, clubs. Okay, now each one of those suits contains 13 cards. I know 13 because 52 divided by the 4 suits is 13. So they are an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then a jack, a queen, and a king. Now for what we're going to do, we're going to consider these face cards. Everything else is a non-face card. These are your face cards because they have faces on them. Okay, an ace does not have a face on it, so we're not going to consider it a face card. Now we've excluded the jokers from this deck because we're not going to play poker with the jokers in them. Okay, you can, but we're not going to. Alright, so this is where we add the extra layer to it. I've got two problems here. And what we want to do is we want to find the number of possible 5-card hands that contain the specified cards. So you might need to know a little bit about poker here. A full house is when you have 2 of one kind and 3 of another kind. Okay, so I want a full house of 7s and 3s. Well, if I'm just looking at the 7s, okay, I'm going to go ahead and say that's my 2. And that part's not going to matter. I'm just going to designate the 7s as the pair and the 3s as the 3 of the other kind. Okay, if I need 2 7s, there are 4 7s, and I just need 2 of them. I don't care which 2, I need 2, and it doesn't matter which one I get first. It could be the 7 of hearts and the 7 of clubs. It could be the 7 of spades and the 7 of hearts. It really doesn't matter. I just need 2 of them. So 4, and I'm choosing 2. Okay, I'm going to use my shortcut here. 4, 3. I'm going to count up. 1, 2. Okay, that's really 12 over 2, which is 6. So there are 6 possible combinations of me getting 2 7s out of that deck. Now I'm going to do the 3s. For the 3s, it's 4, choose 3. 1, 2, 3. 4, 3, 2. 1, 2, 3. Okay, these happen to cancel, so I'm left with 4 over 1, which is 4. Okay, so I'm just looking at 7s and 3s right now. I haven't put the full house together. I have 6 combinations to get 7s, 4 combinations to get 3s. Now, what I want is the total hand, and this is where it changes now to a fundamental counting principle problem, because I don't care which of these 6 goes with which of those 4 possibilities. I just need to have the set. So I'm going to do 6 times 4. Again, that's what I'm doing. Like, if I'm thinking about it as a tree, here's my hand. I have 6. 1, 2, 3, 4, 5, 6. Good. 6 options for my 7s, and then each one of those could have 4 options of the 3s to get. Okay? So I would multiply those together, and that tells me that there's 24 possible hands of getting a full house of 7s and 3s. Okay? We're going to do one more here. We're going to do a 4 of a kind in 5s. 4 of a kind is exactly what it sounds like. Okay? 4 of the same thing. Now, I have to have 5 cards total, so there's a 5th card here, and I don't care what that is, but it can't be a 5. So, my 4 of a kind. I have 4 5s, and I'm picking all 4 of them, and I don't care what order I get them. I just have to have them all. So really, this is 1, 2, 3, 4, 4, 3, 2, 1, 1, 2, 3, 4. Everything cancels here, so I just have one possibility, which makes sense. If I'm going to get all of my 5s, there's only 4 in the deck. As long as I have them all, that's one group of 5s. Okay? My last card in that set has to come from the deck, and I don't care what it is, it just needs to be something else. I've already used all my 5s, so now I have 48 cards left, and I'm picking one of them. Okay? One blank, 48 over 1, so I have 48 possibilities for that other card. Now I change it to a fundamental counting principle problem. Okay? I have the first part, and there were 4 options for it. Sorry, 1 option for it to get all 4 5s, and then 48 options to get that other card. Well, 1 times 48 is 48. So there's 48 different possible hands that I could have with the 4 of a kind and 5s, where that 5th card would be something else. Okay? This is the part that I think we'll struggle with the most. I don't think we're going to struggle with combinations themselves or putting them in the calculator or anything like that. It's when we do these card problems and change it into the fundamental counting principle afterward. So if you have questions, make sure you submit those to the discussion board or shoot me an email. And good luck on your assignment.